it's quite a pleasure that the organizer to invite me to this conference. I thank you. It's a pleasure to visit Russia, and I think this is my 5th time to visit Russia, but this is the 2nd time to visit MIPT, but this is my first conference, to attending a conference here. So my topic is efficient neural computing on edge. And my major is for computer vision. So basically, the examples I present here in the slides focus on computer vision, especially the convolutional network. So this is some outlines of my speech. So first will give some brief history about neural computing on edge. For example, some applications and some businesses, because I'm from the business industry. So the second part is that, for example, the hardware, the chipset, and the toolset for developing the neural computing on the edge. So the second part is that the general methodology and the techniques will introduced. For example, some general practice in the research community and also in the industry. And I will introduce some of the network design, efficient network design, and also the compression and pruning for neural networks, and the quantization. So and also distillation, basically the teacher-student model, trying to, with a larger network, trying to teach a smaller network, and the small network can run on the edge. And also I will show you some of the recent research and the engineering investment in Huawei. So basically it's our work to contribute to the community. And last I will propose some of the challenging problems, because still a lot of problems we need to handle in the future for the computation on the edge. So let's go into the presentation. First, we can see the market and applications. So from some consultancy, there's this kind of estimation in the future. In 5 years, there will be 16 billion gadgets, AI gadgets, with AI capabilities. That's your cell phone, the camera, and also the car that will have the AI capacity in the future. So that means that at least, for example, in this estimation, there will be 20% per year increase. So continuously, that will be a big industry. So big industry introduces a big opportunity for example, here, there's also a lot of enterprise and the startups in China. This is an overview. For example, most of them are startups. For example, investing in, for example, like hardware, chipset, and algorithm, platform, etc. So it's a booming industry, and a lot of people working on this subject and doing engineering on this subject for just in several years. So it should be, for example, like tens of billions US dollars business in the future, especially for the algorithm part. So why we need to do an AI on edge? So you need to consider this four parts, for example, 4 criteria that you need to consider in the future. For example, the first part is that how you can collect your data. Right now, the neural networks, for example, the deep neural networks, needs a lot of data. But usually on the edge, you only collect some data, for example, personal data or some limited data which is not pulling together too big enough to train the neural networks, especially when the neural network is deep. When you need to train a neural network, you usually have millions of examples, labeled examples, which are lacking in the edge. And this kind of lacking of data will be a first criteria that how you can to decide your algorithm is running on the cloud or on the edge. On the cloud, usually you pull in the data together, and you have lots of labeled data, and you can train the network on the cloud with a lot of computing resources. But on the edge, definitely that would be a problem. So the second part is latency. So if you train a network on the cloud or doing inference on the cloud, which usually the latency is quite big. For example, if you're trying to handle this kind of autonomous driving problem, which will be definitely a problem because of the latency of the connection to the network data center, which is not a huge advantage for this kind of critical applications. So if your task is not that kind of latency critical, you can do it on the cloud. But if it is latency critical, especially for some industry tasks like autonomous driving, or you control some of the machine that's working on the manufacturing or something. That would be quite critical if you need a very low latency. So latency is another criteria you need to consider if the AI should be running on the edge. The third part is the bandwidth. Right now, Huawei is pushing the 5G to the industry, but still the bandwidth is still a huge problem because the data is huge. Right now, the video is like for each second, the camera can generate gigabytes of the video if it's high definition, so uncompressed video. So basically, the bandwidth still will be a problem. So in the future, if your tasks are limited by the bandwidth, or also the bandwidth could be expensive in the future. For example, if you have this kind of a task that need to continuously streaming the data, that will be a little bit expensive. So so the bandwidth is the third part, and the last part is autonomy. So basically, if your applications need the devices to be, for example, when the network is down, it can be also fulfill your task in the future. So that will be, we call this kind of task like a critical for a device. So basically in these devices, they need to be autonomy. So you need to running the AI on the edge. So trying to save this kind of, situation when the network is down. So when you go through these criteria, that obviously there will be lots of applications that need to run it on the edge. So this kind of requirement brings new opportunities, and for the hardware, for the software, for the algorithm. So there will be a new semiconductors that will be dedicated to this kind of computing, right? So a lot of the companies right now are trying to develop a new chipset for this kind of neural computing, especially for computer vision, for language processing, for many other stuff. So basically, we also need new frameworks for AI processing, especially for inference engine. So we are trying to not to invent the wheel repeatedly. So there will be this kind of engine trying to, when you have this kind of model, you can run it on this engine. So the engine is also some of the battleground for the community and also for the industry. And the last is the algorithms for different applications. There will be a lot of opportunity here. So basically, you need to design efficient neural net models for specific tasks. So this will be the three opportunities for the researchers, engineers, and the industry. So we will go through this. First, we will go through these three aspects, and then later on we will focus on the algorithms. So, for example, the first part is the chipset or the hardware. So, if you are trying to have this kind of edge AI computing, so basically you need to have specific AI chipset dedicated to it. For example, here we have some. Can you see the? Okay, here. So here we have some. No, I think I'm not connecting to this one. So basically, I will use this one. So you will see some traditional players here. For example, the Intel and AMD, NVIDIA. A lot of people must be using NVIDIA, for example, the GPU to train your network. And also, Huawei recently going into this business, and also Alibaba, and a lot of startups here. So basically, they are designing ASICs for dedicating to inference. So lots of American and Chinese startups working on this part. And why they are choosing ASICs, later on I will provide some opinions here. And also the FPGA and also other, for example, specific neural computing. For example, Qualcomm previously, and also IBM, trying to develop the spiking neural networks devices that will be using for directly, specifically towards the spiking neural networks. So, yeah, so there's lots of players here. So the key observations for the industry here is that only a few, most of the except only a few. Most of the chipsets are designed for deep neural network right now. So for spiking neural network, for example, IBM doing that 10 years ago maybe, and Qualcomm 5 years ago, and they see limited applications there. And also there will be a lot of difficulties for algorithm. So there's not much opportunity for the business there. So spiking neural networks have little voice in the community, but recently they are coming back. So the second part is that most chipsets are designed for edge, actually. So basically for the second part, for example, for ASICs and also for FPGA, lots of investment are put into the inference part. So for training part, right now, I think NVIDIA are dominating this business. So Huawei is a newcomer, and also Alibaba is trying to get into this business, but still compared to NVIDIA, is still very limited capabilities in training part. But for inference part, there's a lot of players here, and they gain lots of opportunities because for inference, they are towards different applications. These different applications bring different chipset requirements. So there's will be so a lot of business are booming here, and also we can see that lots of startups. And even Huawei are trying to investment on the ASIC part because ASICs are power efficient. And when you, for example, for one specific operations, the ASICs can run it on a low power edge and and a higher frequency. So basically, they are relatively low power consumption. And also, the ASICs is a little bit not less flexible compared to the GPU and also the CPU, because CPU and GPU are kind of general computing devices. But for the ASICs, there are some limitations. For example, the pipeline and operations, there will be limitations. But while the industry invested on ASICs, because the neural networks right now, for example, the convolutional networks, the recurrent neural networks, basically they are this kind of structural layers by layer computation could be easier for which is not general computing, but easier, for example, for ASICs to carry out this kind of operation layer by layer. So this kind of not less flexibility also not a disadvantage for ASICs. So right now, a lot of people invest on ASICs right now. Oh, why I getting back? So I don't know why. Let me. Something happened. Oh, I don't get the next slide. Why? Let me do this again. Okay, yeah. So the second problem is the platform. So I think a lot of you might get acquaintance to the images on the cloud, especially, for example, TensorFlow right now is basically the industrial standard for neural network training and inference on the cloud. There will be a lot of candidates here, for example, like Keras, the PyTorch. Recently, PyTorch from Facebook are increasing in this market because a lot of researchers using PyTorch doing their research. And a lot of students use it, so it's increasing right now. But still, the TensorFlow is the basically the standard for industry. But for the edge, which is totally different. So basically, a lot of players are here. None of them are dominating this business because for edge, people are usually more concerned about the inference and the efficiency, and also this kind of power consumption could be critical for many applications. So different hardware, different devices, they develop their own inference engine. And for example, here you see the TensorFlow Lite from Google, which is designed for mobile, especially for the ARM CPU. And NCN is developed by Tencent. And also, Pada Mobile is developed by Baidu, and the MMN developed by, I think it's for Alibaba, maybe. So there's a lot of players here, which is totally different from the cloud. So, for example, a lot of engineers working specific applications, they use specific chipset, so they need to use specific inference engine to speed up the whole process. So basically, there's more diversity here in inference engine on the edge. There's some little bit delay, I think. No? Why? Let me do this one. Sorry for that. Duplicate. Yeah, it would be much better. Okay, so this is some overview of the inference engine. So basically, these inference engines are used by the industry, and a lot of researchers, if they are dedicated working on the algorithm design for devices, they will be using this inference engine for the business and for research. So. And then last one is the algorithm. So there will be a major topic here. So these are the general methodology and the techniques, or we so-called a routine we are doing in the industry. So basically, when you're trying to do design a neural network and trying to run the applications on the edge, for example, which is running on a smartphone, for example. So firstly, you train a larger network, for example, for object classification or object detection. You will have this 100 layer of the CNN network, and which is training on the cloud. And then the second part is you need to have an efficient network design. So basically, which is with less parameters and with fewer layers, fewer filters for each layer, something like that. And when you have these two things, you have this kind of teacher-student model trying to distill this kind of knowledge from larger network to the smaller network. So basically, the smaller network have this guidance through by this kind of larger network trained on the cloud. And after the training, you have a smaller network, which is with similar performance with the larger network sometimes. And sometimes which is not that good, but still it's workable because when you have less parameters, usually there will be some performance loss. And after that, you can do compression and quantization. So the building blocks, the routines here, when you do a specific task, it will be not necessary to go through all these kind of building blocks. So maybe you need to skip the compression or quantization because it's already met your requirements. That's okay. And also, there will be some of the trade-off between these building blocks. So this is basically the general pipelines for efficient neural networks for industry. And a lot of researchers in this area trying to investigate the problems in these 4 building blocks. So I think it's, the 4 building blocks is here, for example, for efficient network design and for teacher-student model, which is called the distillation by someone, and also compression and the quantization, which is the major topics in efficient computing on the edge. So these are some of the examples from the literature. So basically, for example, in 2017, the Google proposed this so-called mobile net, which is trying to decompose the convolution layers into, for example, this kind of depth-wise convolution and also combined with point-wise convolution. So this decomposition trying to minimize the feature map between, minimize the data movement between the layer by layer. So basically, there's fewer parameters and a little bit less computation. The big part, the major concern in the efficient computing on the AI usually come not for computing, but for the data movement inside the DRAM. So basically, it's quite close to the devices. So if you have lots of data moving back and forth in the DRAM, there will be lots of latency and also power consumption. So I think the method here are trying, basically the guidelines here are trying to decrease this kind of data movement in the DRAM. So basically, that will be again a lot of advantage for latency, for power consumption, etc. And also, similar methodology I use for ShuffleNet, basically, which is proposed 1 year later and by a Chinese company. Basically, they have different techniques using group convolution and channel shuffling, trying to maintain for the feature map, trying to maintain this kind of representation power when this convolution is decomposed. So basically, these techniques can also date back to, for example, later, earlier design, for example, like a squeeze and squeeze net, something like that. So basically, it's a similar idea repeatedly proposed by the literature, but the key here is trying to minimize the data movement inside DRAM. And also there will be some more dramatic change in the network. So here is one of example proposed by, I think by Berkeley. And they're trying to replace the conventional convolution with this kind of a shifting operation. Basically, they don't do any computation, no addition, no multiplication, but trying to just slightly move this kind of feature map, trying to use this kind of shifting operation to replace, have the similar effect on with the convolution. So it's supposed to be, for example, if you implement it carefully, if there's some hardware that can dedicate to this kind of operation, that will be dramatically reduce the movement of the data and also the computation power. So basically, this is one of the examples that dramatically changed in the design of neural networks. So I think these three examples are human designed neural networks. Basically, it's handcrafted with a lot of human expertise. So they need a lot of experience on specific field. For example, you need to quite familiar with the computer vision if the network is designed for computer vision task. So there will be need a lot of research and long time of this kind of experience to design these networks. So recently, the challenge is to how we can design a platform or routine that can automatically design this kind of a network. So this is proposed by Google, I think, from 2017, 2 years ago. So basically, they're trying to develop a search method, basically trying to search a better component for a network. So first, you need to design a search space, for example. So the search space can be, for example, how many layers or how many filters in each layer, and how this layer can be connected together. So there will be a lot of variables in the search space here. If you design the search space, you can design this kind of search strategy. So basically, you sampled the network from these search spaces, and then doing the training and evaluate the performance, and then feedback to this search strategy, trying to get a better one, better sample, which is have little bit higher performance. So this procedure can be repeated again and again. So eventually, you will have a better perform neural network, which is this routine basically trying to optimize the neural network design, which is quite a hot topic recently for the community and the industry, because usually for industry, and because the industry have a lot of computation power, usually this kind of routine needs hundreds of GPU for several weeks to get a new, better, efficient network. And recently, also a lot of research are dedicated to design less, for example, power resource consumption framework for automatic search. So basically, for example, they develop a differential framework, which is here we call DARTS. So you can search the original paper, which is far less than the original one. For example, they can only use 1 day or several GPUs to get a better result than, for example, than human design. So the search strategy can be differential or non-differential. For example, the first one using reinforced learning, trying to basically it's optimized problem trying to solve by reinforced learning. And also recently people are using evolution algorithm, which is a quite traditional evolution algorithm, are applied to this problem, trying to optimize this kind of performance to strategy pairing of the problem. So, interestingly, that Google found that evolution usually have better results, converge faster than the reinforced learning. I think it's quite common because reinforced learning usually the feedback is only one value, which is the return of the one value, which is the performance of a network, which is only a little information in this part. So the convergence of these kind of methods could be quite slow, but evolution could be faster than reinforced learning. And also, recently, also the people more care about, for example, not only the performance of, for example, accuracy of the neural network, but also the latency of the network. That's basically the key concern for the AI on the edge, because you don't you remember the latency is one of the concern we are doing when we are doing AI on the edge. So basically, right now, a lot of people not only caring about the performance, also the latency or other stuff. So basically, this kind of multi-objective search problem are proposed. So basically, they are using this parallel front, trying to have this kind of curve. So you can select, so the user or the application can select one. For example, we need this kind of flops and with this kind of performance. So there's a lot of choice here. So here is one of example recently doing by the industry. For example, here the efficient net is, I think this year proposed by Google, which is have the best performance on the classification, which is far better than the human designed neural network. So with less competition and less resources, they can gain much better, not much better, but better performance on the ImageNet classification. So next is the pruning and compression. The pruning and compression basically is proposed, I think, dates back to the 2016. The original devices is using the Qualcomm's CPU, and the pruning basically the idea is that the neural networks, especially the CN convolutional neural network, the weights, they have lots of redundancy in the weights. So basically, we're trying to remove some of the redundancy in the neural network and trying to gain speed up of the neural network. So the idea is quite simple. For example, you're trying to make zeros in the weights. But actually, in many applications, this kind of setting some of the weights to zero don't minimize the computation and also the memory usage for a neural network. So here we see the original one. For example, the pruning presented in this paper actually doesn't work well in the actual devices. But the pruning is still a valuable idea because you can prune the whole filter. If you can prune the whole filter, for example, remove the whole filter, basically will be work for the CPU computing or GPU computing, which is basically save some of the parameters and also save the computing. And another way recently we are working on is trying to remove some row of the filter. So if your devices are dedicatedly designed to this kind of operation, it can have some benefits to for example, to speed up or minimize this kind of usage of the memory. So pruning and compression basically, I think, is not that good method you can directly use in the industry because it very depends on the device, how the device is designed. So that will be, for example, if you develop a technique, usually that technique are dedicated only to one of type of the devices. So so basically, there will be a lot of engineering. So that will be. So I think the another methods here are quantization. I think a lot of colleagues here, especially my colleagues in Moscow's data center, are working on quantization. The idea is trying to quantize the weights and activation. Basically, previously the neural networks are represented by weights with the float numbers. But right now, if you can represent the weights by integers or even the binary numbers, that will save a lot of parameters and also computation. For example, when the quantization go to extreme, which is a binary quantization, so the computation here are only counting the number of 1 and zeros. So basically, there are no addition, there's no multiplication, so there will save a lot of computation in the inference. So, but the problem is that how we can quantize the float value. So you need to find some good formula to quantize these values, and also how to train a network. So there is two ways to do that. For example, training a quantized network from the scratch, or from another. For example, if you have a trainer network, you can quantize the weights. Let them do a little bit of fine tuning. So, and also the quantization are quite closely related to the hardware. So how you can implement this quantized network inference to specific devices are quite vital to the engineer and also to the researchers. So usually many quantized methods are not supported, for example, for the recent devices. So you need to be careful in this part, because actually you see a lot of papers working on that, but the real implementation could be difficult. So here are some examples from the community. For example, in 2016, there's a binary network from Mila, I think it's Benjo's team, and also BM Plus, which is our work, and also XNorNet, which is dedicated to the computer vision. Lots of people using that, for example, for image classification, also detection, something like that. And also Dorefa, which is, I think it's also 2017, maybe. So, and many a computation problem can be formulated as a hyperparameter hyperparameter optimization problem. So how you can quantize a value, which is you will have lots of choices of the parameters in a specific formula, and also there will be design, for example, how the bitness of each layer, how you can quantize this layer, which is a lot of choice. So this kind of different choices create a hyperparameter space. So how to optimize this kind of problem through this hyperparameter space, which is an optimization problem. And previously, the efficient network search basically is also one of the optimization problem. And the similar structure can be solved by RL or by evolution with the quantization. And the last thing is the distillation or teacher-student model, which is trying to teach a smaller network with a larger network if you train a larger network with enough data. So I think this idea comes from Hinton, and previously they show us how, for example, this kind of so-called dark knowledge, which is meaning that, for example, here is a classification problem. So basically, you're trying to classify the images to four categories. So basically, the idea is, for example, the dog is definitely not cat, right? But it's the similarity between the dog and the cat basically is closer to the cat to the car, right? So, but this information usually in the training are not used by many algorithms. This kind of information is not used because previously they think it is a categorized problem, so it's 1, 0. So basically, these two categories they think they are similar, but the dog and cat are more similar because the softmax output here is 0, 9 and 0, 1, which is closer, but the car is not that similar to the cat and dog. So this by employing this kind of information, and Hinton and the team make this kind of distillation are more efficient, converge faster, and get better results. And this idea are still, I think, the most criteria for the distillation. So there's not many research topics on this specific, for example, distillation problem. We can only find a few researchers here, but still, which is quite important and a good problem for investigators in the future. So later on, I will introduce some of the work we are doing in Huawei, especially I think date back to the 2017, because we have a lot of business related to the cell phone. So Huawei right now, I think, is the third largest, the second or third the largest cell phone manufacturer in the world. So, so basically, we care a lot about the efficient computing on the cell phone. So we do a lot of work, for example, trying to design new convolution filters or design new pipelines to generating this kind of a feature map using limited resources on a cell phone. So versatile filters, which is I think we published in 2018, which is design a filter which can use a large filter repeatedly. For example, using this larger 7x7 filter, a convolution filter, you can get a lot of smaller filters with the same weight. So you can using one single large filter to generating different kind of feature map. So trying to minimize the parameters are using in this kind of computation, in the process of computation. And later on, we developed idea trying to bring different kind of masks into large filters, trying to create more feature maps. So again, trying to decrease this kind of parameter use in the computation. And we found that, for example, the previous three work are not working well for ARM CPU, because still there will be lots of operations are not supported by ARM CPU. So if you need to do that, you need to redesign the chipset, but that will be very costly. We are thinking about that, but that will be very costly. So later on, we switched to how we can create or find a new cell, which is by building by the already supported operations. So trying to use this kind of, we designed this ghost cell. I think this paper are published this year. So which is gain better performance than Google's, for example, EfficientNet. So and this problem we are trying to do is that directly testing it on our cell phone. So basically, when you design a network, you can directly deploy to the cell phone and to some specific applications. So here the idea is that the design handcrafted cell will be more meaningful than design, for example, dramatically design a new, for example, new convolutional filters or different operations. Which is, so how many times I left? So let me check out. Yeah, it's still have some time. So I think I can quickly go through it. So here also row pruning, trying to prune some of the rows in the convolution filter, which will speed up the process of the computation. But this kind of pruning needs dedicated hardware to support this kind of row pruning, which is also a task we need to cooperate with the chipset designing team. So basically, that will be work in our next cell phone. And also distillation. Distillation is an interesting problem. Usually, the distillation is not working as the research community thinking about. In many applications, original distillation needs the data to help the original labeled data trying to train the smaller network. But here we develop a method trying to don't use the data to do this kind of distillation. And the idea is trying to create a GAN network, trying to trying to make the output of the smaller network and the larger network, they have a similar output distribution. And this kind of training can be repeatedly using this kind of a GAN mechanism, so they can merge together with the training of the distillation. So, and last is for quantization. We do a lot of work on quantization, and we have a huge team working on that, because there will be a lot of implications for quantization. Especially, we are investigating this problem. If the quantized network can have the capacity of the full processing network. For example, if you have a full processing network, can we find some quantized network with the similar performance? So we do a lot of experiments. For example, here we testing on an ImageNet. We can see that if we have more neurons, for example, like 3 times of neurons compared to the original network, we can basically get similar results for a quantized network, which is a huge implication here. So we can design a totally new chipset only dedicated to binary operations, which is more will be much faster and power efficient than, for example, right now, the chipsets we are they're working on the floating values. So that's our I think still a lot of work to do, but the implication for future hardware in this part is quite huge. So another work here we are doing is trying to develop a new efficient framework, trying to search a better cell or better structure for a network. So here we develop a PDOT. Basically, it's only use 0.3 GPU days to search a better, automatically design a neural network, which is better than, for example, for a lot of human handcrafted networks. So the idea is here that we have some observation that for many of the differential framework for search, for neural architecture search, we found that the skip connection could be quite vital in this framework. So basically, the algorithm trying to overfitting the data by adding lots of skip connections. So this kind of basically this kind of results will be very harm to the final results. For example, trying to, which is basically overfitting the data, the training data, but the generalization of the neural network could be lacking in the future. So we try and solve this problem by this kind of progressive dots, which is we gradually increasing the number of the skipness and trying to solve this problem. So finally, we try a lot of work we are doing for the AI on the edge. We trying to develop a framework which can automatically design the network for us, and which will be if we can find a neural network through this framework, and we can deploy this neural network directly to the devices. So basically, it's an automatic framework we are working on. So here we created this kind of hardware in a loop system. Basically, if you sample one of the network from the search spaces, and we directly deploy this kind of network to our cell phone, and trying to look into the latencies, the memory usage, and those values will return back to the this kind of the search strategy. So basically, it's a multi-objective reward, and this kind of reward can be can be solved by, not solved, but basically optimized by this reinforced learning mechanism. So trying to bring this total pipeline into full automatic. We are still working on it, but it's quite promising in the future. So here we're trying to wrap up the speech. So basically, there's no free lunch in this kind of AI on the edge. There will be a trade-off between efficiency and the generalization of network. Usually, when you train a smaller network, the generalization for example, on the future data will be decreasing. So how we can solve this problem still quite challenging. I think a lot of people are working on that right now. And also we are hitting the memory wall. Basically, the memory movement in the DRAM is the key problem trying to design a neural network on the edge. So how we can minimize the kind of movement, which is quite vital for power efficiency. So here you can see that the data movement costs more energy compared to, for example, to multiplication and adding for this kind of computation in the neural network. So another quite interesting theme is that a spiking neural network is coming back. So if you guys are trying to work on a spiking network, definitely there will be some hardware to you can design for this kind of task. So this is a challenge. I think a neural network search seems promising, but however, still a lot of controversy right now. So it's not better. Google, some of researchers in Google argue that this kind of automatic optimization is no better than random search. So it's quite interesting. So how we can design larger, more general search space, which is still a not solved problem, and how we can efficiently evaluate the sample architecture is also vital. Because right now you need to train a network, and until it converges, it is very time-consuming and also energy-consuming. So quantization is closely related to the hardware, and I think the equivalence problem is quite vital. For example, here we propose to the and how we can limit the operations here, and will be benefit on hardware design, and understanding I think all these problems will wrap up to the key problem here. We don't understand the deep neural network. And we don't know how to quantize the capacity of a given structure of a neural network. If we can solve that, I think a lot of problems here can be solved. So yeah, I think I finished. Okay. So open to questions.
Thank you very much for extremely interesting lecture. So we have 3 minutes. Professor Terehov, please.
Okay, yeah.
And then your answer.
Okay, yeah.
So my question is, when you spoke about automatic design of efficient systems, efficient architectures, you mentioned that you actually reach a Pareto form of multi-objective optimization. Analytic part of work can stop here, but decision maker should make a decision as a one point. Is it any progress in decision making, not in analytical part, but in decision making? Thank you. Вопрос следующий. Когда решается задача многопараметрической оптимизации, то было отмечено, что достигается фронт Парето, а там, естественно, много вариантов решений. А тот, кто принимает решение, должен выбрать одну точку. И вот есть ли сейчас в этом прогресс систем, которые позволяют принять именно решение?
It's a very good question here. So I think a decision problem is totally different from what I'm talking about here, because my research mainly focused on computer vision. Basically, it's a perception. There's no interactive with the world. So basically, it's not a decision problem, but basically a perception problem. I think a decision making right now, only a few people using, for example, the deep reinforced learning to trying to solve the problem. I think for that part, still my framework will working, because usually this kind of deep reinforced learning, the deep neural network are working towards perception part, but not the decision part. So actually, that's a good topic. I think it should be investigated in the future. But right now, I think in my knowledge, there's only very limited investigate on that part. Yeah, definitely. Yeah, it's a good question.
Any other question?
Thank you for the talk. So you said that you spend much time on quantization of networks. So what precisions do you consider as main targets? Is it only about binarizing the network, or also like using other precisions, 4-bit, 8-bit digits?
Yeah, I think do we need to translate to Russian? So yeah, so basically, we try a lot of quantization. For example, 1 bit, 4 bit, and 8 bits. So for basically the goal here, I think the goal is the same, trying to make the quantized network with the similar performance with the compared to the full procession neural network. But I think the previous research and also engineering are towards, for example, trying to came from a similar structure with the original one. For example, I have a structure of a full procession neural network. We're trying to quantize this network and the resulting network with the similar structure. But our research shows we don't necessarily try to do that because we can change the network structure. For example, make the layers more neurons and trying to solve the similar problem. So that will be broadening the options here. So, but definitely I think 4 bits, 8 bits, and also 1 bit are useful for different type of devices. That totally depends on what the operations and what the device are supported. If your device, for example, your specific designed chipset are supporting 4 bit, you want to go 4 bit, right? Also, you can, for example, go 1 bit. Right now, a lot of people trying to solve this problem by software. For example, you can design a binary network and trying to compact this bitness into one integer or something. So that will be some software solutions here, but actually, if you're trying to save a lot of energy and make it more efficient, definitely the quantization will closely relate to the hardware design. Yeah.
Thank you very much. Unfortunately, we have no time for discussion.
Yeah, thank you.